Hi everyone, welcome to another video for Research Design and Analysis, where today we're going to be talking about issues of measurement and different types of data. So measurement refers to the comparison of some value to a standard, where we might say, we have p units of k. Another way to think about that, right, in less abstract terms, is we can only have half an inch if we have some agreed upon definition of what an inch means. So anytime we're taking a measurement, we're taking something either kind of empirically out in the world or even a more ambiguous hypothetical construct and trying to measure the quality or quantity of it relative to some agreed upon standard. So this could be, your degree of extroversion as something that we can't directly measure, but we can still measure through psychological assessments. Or it might be something more objective, like your height in inches, right? In either of those cases, we need some standard for, units of extroversion or units of dimension, right? And then we can say, well, this is your dimension. This is how much extroversion you have. This is how much height you have, right? And the data that we obtain are the result of this kind of measurement. And in statistics, we're usually measuring these variables in samples of data because, again, it's very hard for us to get access to the full population we might like to study. So that means we're usually going to be taking a sample and we have two jobs. First, we want to richly describe what is happening in the sample that we have. And second, we're often going to want to try to infer something about the population based on this sample. So why do we care about the types of data that we have? Well, the reason is that the type of data that we have determines mathematically what we can do with it and what operations are meaningful and what kind of information we can extract from that data. So let's think about color as an example. Color, right, can be viewed as a spectrum, right? Wavelengths of light give us color, and color then is a continuous interval variable. And we'll get into a little more detail about what interval really means later on. But the basic idea here, right, is that I can go up by 1, micrometer in terms of wavelength, and that has the same value as going up by another micrometer in terms of wavelength. So each micrometer is the same distance, but as I go along this scale, how those wavelengths of light appear to the human eye change. An alternative view of color is to think of color as a discrete nominal variable, right? So this is how we use color linguistically. We have red, yellow, green, blue, purple, right? Now, where does green end and begin? Well, that's an open question, and it's kind of a fuzzy category. These nominal discrete categories don't map perfectly onto the continuous interval values. And in fact, the culture that you grow up in can actually have a substantial influence on how you perceive these color boundaries. And not everyone has the same definitions of blue and green in different places of the world, right? So color can be viewed in either of these ways, but then we get into kind of interesting issues when we try to place other colors, right? So we said, okay, generally, like red has a rough kind of wavelength to it, even though we don't necessarily agree on where the boundaries are. But okay, how many categories of color are there? Down in the continuous scale, there's no categories. It is a spectrum, right? You can be anywhere along there, and you can take any value along there. On this nominal scale, we only have 5, but we could have 6, right? We could have 7, we could have a bunch. And after a while, as we kind of line those things up, our variable is changing from something that is more nominal and discrete into something that is more continuous and interval. So some types of data can really change depending on how we look at them. Other types of data have pretty fundamental properties that mean we have to treat them in a specific way. So when we're classifying these types of data, we'll often break them into non-parametric and parametric. And those definitions are a little bit technical. So I'm going to kind of ignore what non-parametric and parametric really mean right now. But the shorthand of it is that non-parametric is going to cover those things that are more discrete and don't necessarily obey direct probability distributions. Okay, so for example, we have nominal categories. So these are things that are mutually exclusive and qualitatively different, right? So in Canadian politics, these might be your major parties that you're choosing between, right? And your political affiliation, we could maybe vaguely line these up from left to right in some kind of spectrum and rank order them, but they really are discrete and qualitatively different, right? The Green Party isn't twice the Liberal Party, and that's not, a negative of the Conservative Party, right? There aren't really mathematical operations here. All we can really say is that these things are not equal. Similarly, gender is another one where we have mutually exclusive, qualitatively different categories. And again, there can be good debates about, exactly how we want to think about this variable, how many categories there are, should there be none, should there be many? Traditionally, right, in a lot of census data, we only measure 2, right? But in any conceptualization of gender, you're usually only falling in one of the categories, at least at any given time, right? Although your sense of gender identity might change over time. But at any given time, you're only falling in one of those categories. Similarly, ordinal data, right, is non-parametric, but this still is kind of a step above in terms of information that we have for nominal data, because we have quantitative differences but no fixed intervals. So things like ranks are a good example of ordinal data, right? Whoever places first versus second versus third, whoever placed first clearly won, they beat whoever was second, and whoever was second beat whoever placed third, right, and anyone else below that. But we can't say that a person who is, the difference between second and first is the same as the difference between second and third. They're above each other, but they're not necessarily the same order above each other, right? And military ranks would be kind of a similar thing, right? You start at a certain basic level and you get promoted, but the difference between, a private and a corporal is not the same as the difference between a corporal and a master corporal. And that's not the same as the difference between a master corporal and a sergeant. At each step here, they outrank the person below them, but that isn't to say that it is kind of an equal distance in those orders. Now, parametric data, on the other hand, are data that obey, fixed distributions. So there are parameters to those distributions, like a mean and a standard deviation, that is well established, and we can describe the behavior of those data with a distribution. And broadly speaking, that's the difference between parametric and non-parametric here. So the first type of data we have in the parametric category is interval data. So this is adding information again beyond the ordinal, where we have fixed intervals, but there's no true 0 point. So temperature is an example of this, at least as measured on the Celsius and the Fahrenheit scale, right? Where we have the difference between, 200 degrees and 201 degrees Fahrenheit is the same as the difference between 201 and 202 degrees, right? 1 degree is 1 degree, regardless of which scale we're on. Now, we can have negative numbers here as well, but one of the critical differences between interval data and ratio data is there's not really a true 0 point here, in the sense that 0 degrees Fahrenheit is not the absence of temperature, and 0 degrees Celsius is not the absence of temperature. If you switch to the Kelvin scale, then that actually becomes ratio data, where the 0 point really means, yes, there is an absence of this, right? So the 0 point becomes more meaningful in that sense. So we have fixed intervals here, but no true 0 point. Similarly, dates are a good example of interval data, right? So, the difference between March 2nd and March 3rd is the same as the difference between March 3rd and March 4th. Those are 1 day, right? So those intervals are 1 day apart, but there's not exactly a 0 point on when dates occur. We generally have before the Common Era, right, or before Christ and Anno Domini, right, depending on the calendar system that you use. But that 0 point is arbitrary. We've decided this is where we're going to start counting positive dates, and before that we'll count negative dates, right? But in general, the distance between units is the same, but there's no true 0 point in these data. Now, ratio adds another level beyond interval, right? So in ratio data, we have fixed intervals and a true 0 point that would indicate the absence of equality, or at least that 0 is meaningful in some way. And you might actually be, for instance, in some things we could be changing direction as we switch from positive to negative, but at the 0 point, it indicates that there is an absence of something. So examples of this might, for instance, be forces that we measure in the joints biomechanically, right? So we can look at your knee extension forces. If your knee is extending forward, maybe that's a positive force. If it's at 0, that means you're exerting no force. And if it's a negative, that means your knee is exerting force in the opposite direction. Right? Similarly, with something like mass, right, we can't have negative mass, but there is a true 0 point indicating the absence of equality. Or something like speed, right? Much like forces, right? Speed could indicate, how fast you're traveling in one direction. A 0 indicates you're holding still, and a negative indicates that you're moving in the opposite direction, right? So we have these constraints on what we are measuring, and we kind of take it for granted that these different units of measurement exist. But it is actually really important to step back and evaluate a little bit where they come from, because historically measurements were often very regional and idiosyncratic. So they were decided by particular rulers or institutions. And, Britain measured things differently from France, who measured things differently from India, who measured things differently from China, right? Now, these measures were very useful, and they allowed a lot of farming and agriculture and trade to flourish. But they weren't standardized across cultures or across institutions. And this led to some problems, right? So we have a number of units of measurements that aren't really used anymore. So for instance, how many hands tall is a horse? Well, that depends on whose hands, because a hand historically was the distance from the thumb to the extended little finger. And in general, human hands are similar in size, right? But somebody with smaller hands could get away with selling you a taller horse, because if your hands are smaller, the horse is more hands tall. Similarly, before we had imperial pounds, there were the avoirdupois pound, which were 7,200 grains of wheat. If it was a rainy season and those grains were heavier, right, then you'd actually have a horse that weighed less. Because if you had heavier grains, now suddenly your pound is heavier, so the horse makes up less pounds. If it was a dry season and your wheat was, not as good, you'd have a lighter pound, which means your horse weighed more pounds. And clearly those aren't desirable properties of measurement, because you don't want your standard to be changing from one person to the next or from one season to the next. So clearly these older arbitrary definitions are flawed. They did some good work, right? But they're not stable over time, not consistent from place to place, and so on. Modern definitions for standard units, we generally try to base on natural constants. And so, for instance, distance, right? Meters are defined by the path traveled by light in a vacuum at the speed of light. And we can say, okay, how far can light travel in a vacuum over X amount of time? That is a standard definition of a meter now that we can actually measure how light is traveling. Time, similarly, is based on electron transitions in cesium, right, which follows Planck's law. So the second has a natural constant as well, where we can say, okay, here is the natural definition of the second, where this is actually a defined standard constant that is not going to be changing over time. Now, mass is kind of an interesting one because it's a unit that we use all the time, but it's one of the last units of measurement, scientific units of measurement, that still doesn't actually have a natural constant. So the kilogram at the moment is based on the standard prototype kilogram. So there is literally a weight that is kept very protected and very safe and remeasured over time, but that is the kilogram. And all other kilograms are based off of kind of clones of that weight, and then kind of distributed throughout the world, and scales are calibrated to it and that kind of thing. But there is a industry standard kilogram. At the moment, I believe there still is not a natural constant that defines what a kilogram is. So how do we use these types of data in different types of research and analysis, right? Well, these things will come up in a lot of different contexts, whether it's historical research and we're looking back and trying to sort of nominally code like attitudes or beliefs of different cultures over time. We can look at, okay, were they holding, sort of feminist beliefs or progressive beliefs? How many people were speaking out about, different things in this culture at this time? Those things we might try to code more nominally, right? Because it's going to be hard to measure them in things that are other than qualitative. We might also have descriptive research where we can look at things in a more interval ratio way, right? So looking at the amount of money spent on budgets, right? But we could also take this data and rather than looking at it as money in itself, we could represent those priorities more ordinally and say, okay, well, where was most of the money spent? Where was the second most money spent? And then we'd be converting from interval information to ordinal information, but that ordinal information might ultimately be easier to understand or more important to understand in some way. And finally, right, we can also use these things in experimental research where we're taking people and we're randomizing them to groups, we're following up with them, and then we're comparing the results to try to understand how a treatment works. And we can analyze all these different types of data in all these different contexts, right? So it is definitely possible to have interval ratio data in historical research, and it's definitely possible to have nominal data in experimental research. But the key thing is whether we have nominal, ordinal, or interval ratio data, that's going to determine the way in which we can analyze those data, right? And what statistical tools are available to us across these different domains of research. So finally, how much do these types of data really matter? The short answer is quite a bit, right? So usually we might use numbers to represent the values of variables. And these numbers are kind of a stand-in. They're a model for the real world. But they have important properties. Sometimes they're relevant and sometimes they are superfluous. So for instance, when we're talking about sex in statistical analysis, right, we ultimately are going to have to make some conversion of categories, nominal categories, into numbers. So for the purposes of analysis, we might code males as 1 and females as 2, but we have to remember that is a convenience of the analysis. Females are not twice males or vice versa, right? That is something in our coding that we are doing. So the properties of these numbers are important, and we have to decide which are relevant for a given variable because that's going to determine what kind of statistics make sense. The scale of a variable then becomes very important. And again, broadly, we can break these things into two categories. We have the non-parametric types of data in nominal and ordinal, and we have the parametric data in interval and ratio. Interval and ratio data can usually be treated the same way and kind of analyzed in the same way. Nominal and ordinal definitely have to be handled differently than the parametric data, and they often have to be handled pretty differently relative to each other. So let's focus on the nominal scale for a second. Which stats are going to be appropriate here? Well, remember that in a nominal scale, any values that we assign to them are just labels, right? We could call males 1 and females 2, or we could call males 2 and females 1. It doesn't matter, because all we're trying to denote is that they are different. There's no structural relationship between the values and the categories that we're trying to measure, right? In terms of these dots, you can think about this as, ideally, we'd like to have them on a number line if we wanted to analyze them mathematically. But in a nominal scale, you can't place them on a number line, because why would one be to the left or the right of the other? It would be an arbitrary distinction, whichever one you chose. So essentially, this is non-numeric data. We can use numbers for coding, but it's really just a placeholder. The only mathematical notation here then is equality and inequality. So two values are either the same or they're not, right? I have two participants who identified as male or they didn't, right? I can't really say much else about their responses or how they relate to other participants. Things are either equal or they're not, which means we only have a few meaningful statistics that we can really calculate here. We can calculate the frequency, right? So we can look at the number of scores of a given value, and we can calculate things like the mode and talk about the value with the greatest frequency. When we go to the ordinal scale, we get a little bit more information, and that enables us to do a few more calculations. So in the ordinal scale, right, values are ordered, but differences, again, aren't really meaningful, right? So this is, years of education, this is military rank, this is how you finished in a race, right? We can say that, people placed first, second, and third, but that does not mean that the difference between first and second is the same as the difference between second and third. So we have, people lined up on our number line now, which is nice. We can place them on that line. We know who belongs on the left and who belongs on the right, but we can't actually tell the difference between any two sets of number lines, right? We don't know if this was the configuration or if this was the configuration. There's no way of knowing that based on ordinal data alone. So we have mathematical notions now beyond inequality because we can actually talk about whether something was greater than or less than, in addition to being equal or unequal. And this opens up a few additional meaningful statistics. So we can talk about like the median and quantiles, right? So who was in the very middle of the distribution, who was in the first percentile, who was in the 90th percentile, right? We can calculate those sorts of statistics, and we can also calculate ranges and interquantile ranges. So we have more information here, right? And we have a different set of statistics than if we had nominal data, but still not all statistics or all methods of analysis are going to be appropriate. So as we move into the parametric forms of data, right, the first one is going to be the interval scale, right? So differences between scores are meaningful. So we can say, for instance, today was 4 degrees warmer than yesterday. But ratios of these scores can be misleading, right? So 20 degrees Celsius is not actually twice as hot as 10 degrees Celsius. And you can actually see this a little more clearly if you make the conversion between Celsius and Kelvin, right? Where 20 degrees Celsius is 293 degrees Kelvin, 10 degrees Celsius is 183 degrees Kelvin, 293 is not twice 180 or 183, right? Also, we can think about this as, like IQ tests, right? So we can talk about a difference on IQ tests. Those are fixed intervals where they've carefully normalized IQ tests so that you only have so many people kind of scoring at each level. But we can't really say that, someone who has an IQ of, 130, or I have to do the math a little bit easier. Someone who has an IQ of 120 is, twice as smart as someone who has an IQ of 60, right? It's not really how that works. In terms of that scale, right, those numbers, yes, those values are double. Those values are twice. But in terms of the underlying construct that you're really trying to measure, that's not an accurate reflection of what you're doing, right? Because again, there's no real 0 point on the IQ scale. So the way you can think about this visually is, again, we can put things on a number line like we would like to do, and we can put, we can say exactly who's to the left and who's to the right. And we can say by how much they differ, right, from left to right. And there's a real meaningful 1 unit change. What we don't know, though, is in terms of our number line, should we line it up here or should we line it up over here, right? Because again, we don't actually have a 0 point. We don't know which of these two number lines we should prefer. All we know is, given this set of points, we know precisely how to line the people up. So this is a big improvement, and it does allow us to do a lot of other computations once we have equal intervals in our scale. So now we have mathematical notions of addition and subtraction, and we can say someone was X points above or X points below another person, beyond just being greater than or less than. So now some additional statistics become meaningful, such as the mean, the variance, and the standard deviation that you're probably familiar with from other data analysis or statistics type classes. Finally, at the ratio scale, right, we have a very similar picture to the interval scale, but we actually have a meaningful 0 point now. So this provides us with a bit more information because, again, our number line is fixed, right? There's no disagreement about where we should line these points up. We know they start at 0, and then we can say precisely how much to the left or how much to the right of that point you belong. So a lot of physical and mechanical properties, again, mass, speed, position, right, can be measured in this way. Now, ratios between scores make sense when we're on this scale, hence the name, because again, that 0 point is fixed. So we really can say that something is twice as heavy or that something is twice as long, right? And that actually has a concrete meaning that maps onto reality relative to the interval scale, where, again, numerically we can say, oh yeah, the ratio of those two numbers is 2, or the ratio between those two numbers is 1.5. But on the interval scale, it's actually slightly misleading to do that because you're not really indicating twice the amount of the underlying property that you're trying to measure. So now we have this mathematical notation of division, which is accurate, and that's why we call it the ratio scale, because now we can divide and multiply and actually have a direct correspondence between our standard and the units that we're trying to measure. So this doesn't really give us any new notable statistics relative to the interval scale. Means, standard deviations, variance, those are going to be the things that we're most interested in here. And that's why interval and ratio data are often treated the same way in a data analysis class, right? Because ultimately the statistical tests that we're going to use probably apply equally to the interval and the ratio scale. And indeed, the interval and the ratio scale are going to be the focus of a lot of what we do in this course, where we focus on parametric statistics, right? Where we know we can use the mode, the median, and the mean, right? We can use the standard deviation, we can use the variance, right? And we're going to learn a lot about statistical tools for analyzing this type of data. In more advanced statistical courses, you might focus on some of this non-parametric data and learn some of the tools for data analysis when you have nominal and ordinal data. We will get into some of it, right? But I think if you deal with this type of data a lot, you might want to seek out some further training. And the biggest takeaway message is if you have ordinal and nominal data, you can't just shoehorn it into analysis methods meant for interval and ratio data, because you're going to get the wrong answer. And that's definitely important to keep in mind moving forward.